I wanna do things fast, wanna do things faster. XGBoost got crazy optimizations, they're gonna blow your mind, you better watch out because they're so crazy. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about XGBoost Part 4, Optimizations. Note: this StatQuest assumes that you are already familiar with how XGBoost creates trees for classification and regression. If not, check out the quests. The links are in the description below. This StatQuest also assumes that you are familiar with quantiles and percentiles. If not, check out the quest. XGBoost is a big algorithm with a lot of parts. And since gradient boost and regularization were covered in other StatQuest videos, so far this series has focused entirely on XGBoost's unique regression trees. So, now it's time to talk about the other parts. These parts are what make XGBoost relatively efficient with relatively large training datasets. In other words, the first three parts give us a conceptual idea of how XGBoost is fit to training data and how it makes predictions. And the last 6 parts describe optimizations for large datasets. So let's start by talking about the Approximate Greedy Algorithm. In XGBoost Part 1, XGBoost Trees for Regression, we had a super simple training dataset and used different drug dosages to predict drug effectiveness. The first thing we did was make an initial prediction, which could be anything, like the mean drug effectiveness, but by default is 0.5. Then we calculated the residuals and fit a tree to the residuals. We did this by calculating similarity scores and the gain for each possible threshold. And the threshold with the largest gain is the one XGBoost uses. Note: the decision to use the threshold that gives the largest gain is made without worrying about how the leaves will be split later. And that means XGBoost uses a greedy algorithm to build trees. In other words, since XGBoost uses a greedy algorithm, it makes a decision without looking ahead to see if it is the absolute best choice in the long term. In contrast, if XGBoost did not use a greedy algorithm, it would postpone making a final decision about this threshold until after trying different thresholds in the leaves to see how things played out in the long run. And this same process would be repeated for every single possible threshold for the root. In other words, by using a greedy algorithm, XGBoost can build a tree relatively quickly. That said, when we have a lot of measurements, then the greedy algorithm becomes slow because it still has to look at every possible threshold. And if we had a more interesting training dataset that used dosage, mass, favorite number, and a bunch of other stuff to predict drug effectiveness, then checking every single threshold in every single variable would take forever. Wah wah. This is where the Approximate Greedy Algorithm comes in. Going back to our example with a lot of observations, instead of testing every single threshold, we could divide the data into quantiles and only use the quantiles as candidate thresholds to split the observations. For example, instead of using the smallest 2 dosages to define the first threshold, the Approximate Greedy Algorithm uses the first quantile to define the first threshold. And the second quantile is the second threshold that we will consider, etc., etc., etc. Note: if we only used one quantile and split the observations in half, then, since there are no other options, that quantile would be the threshold. This would make finding the best threshold very fast since we would not have to calculate gain or similarity to make the decision. But since both sides of the threshold represent a lot of people who have positive drug effectiveness values and negative drug effectiveness values, then this threshold would not do a good job predicting drug effectiveness. In contrast, if we had two quantiles, then our predictions would improve because we would do a better job separating observations with positive values for drug effectiveness from observations with negative values for drug effectiveness. So, for this data, 2 quantiles are better than 1. If we had 5 quantiles, then our predictions would be more accurate since each threshold represents a smaller cluster of observations. However, the more quantiles we have, the more thresholds we will have to test, and that means it will take longer to build the tree. For XGBoost, the Approximate Greedy Algorithm means that instead of testing all possible thresholds, we only test the quantiles. And by default, the Approximate Greedy Algorithm uses about 33 quantiles. Now the question is, why do we say about 33 quantiles instead of exactly 33 quantiles? To answer this question, we need to talk about parallel learning and the Weighted Quantile Sketch. When you have tons and tons of data, so much data that you can't fit it all into a computer's memory at one time, then things that seem simple, like sorting a list of numbers and finding quantiles, become really slow. To get around this problem, a class of algorithms called sketches can quickly create approximate solutions. Unfortunately, explaining the details of sketch algorithms is out of the scope of this StatQuest, but we can discuss the general idea of how XGBoost uses them. For this example, imagine we are just using a ton of dosages to predict drug effectiveness. Now let's move this dataset to the top of the screen and imagine splitting it into small pieces and putting the pieces on different computers on a network. The Quantile Sketch algorithm combines the values from each computer to make an approximate histogram. Then, the approximate histogram is used to calculate approximate quantiles. And the Approximate Greedy Algorithm uses approximate quantiles. Bam? No, not yet. So far, we have described the Quantile Sketch algorithm, but XGBoost uses a Weighted Quantile Sketch. So that means that these quantiles are not normal, everyday quantiles. Instead, they are weighted quantiles. Hey, what's a weighted quantile? Usually, quantiles are set up so that the same number of observations are in each one. In other words, if 10 observations were in this quantile, then there would be 10 observations in this quantile, and 10 observations in this quantile, etc., etc., etc. In contrast, with weighted quantiles, each observation has a corresponding weight, and the sum of the weights are the same in each quantile. For example, if the sum of the weights in this quantile was 10, then the sum of the weights in this quantile would also be 10, and the sum of the weights in this quantile would be 10, etc., etc., etc. The weights are derived from the cover metric that we discussed in parts 2 and 3 in this series. Specifically, the weight for each observation is the second derivative of the loss function, what we are referring to as the Hessian. That means for regression, the weights are all equal to 1. And that means the weighted quantiles are just like the normal quantiles and contain an equal number of observations. In contrast, for classification, the weights are the previous probability times 1 minus the previous probability. So let's see how the equation for weights affects the quantiles in classification. And we'll do that with this simple data set. In this classification example, we are using drug dosage to predict the probability that the drug is effective. The red dots are dosages in the training dataset that were not effective. And the green dots are dosages in the training dataset that were effective. These red and green X's correspond to the previously predicted probabilities that these dosages are effective, and they start out at the initial prediction 0.5. After running the data down the first tree, most of the predictions improve. And as we add more trees, most of the predictions get better and better. Okay, cool. But what does this have to do with calculating the weights for the Weighted Quantile Sketch? When using XGBoost for classification, the weights for the Weighted Quantile Sketch are calculated from the previously predicted probabilities. So let's calculate the weights for each observation. Note, I'm just showing one example of calculating weights. In practice, weights are calculated after building each tree. These predicted probabilities are very close to 0, indicating a high amount of confidence in classifying these dosages as ineffective. Since the previously predicted probability for these 2 points is 0.1, the weight is 0.1 times 1 minus 0.1, which equals 0.09. So let's put 0.09 here so we will remember it. These predicted probabilities are very close to 1, indicating we have high confidence in classifying these dosages as effective. Since the previously predicted probability for these 2 points is 0.9, the weight is 0.9 times 1 minus 0.9, which equals 0.09. So let's put 0.09 here so we will remember it. These 2 predicted probabilities are very close to 0.5, and that means that we are not very confident in how to classify these observations. Since the previously predicted probability for this point is 0.6, the weight is 0.24. So let's put 0.24 here. Lastly, since the previously predicted probability for this point is 0.4, the weight is 0.24. So let's put 0.24 here. Now we see that when the previously predicted probability is close to 0.5, meaning we don't have much confidence in the classification, the weights are relatively large. In contrast, when the previously predicted probability is very close to 0 or 1, meaning we have a lot of confidence in the classification, the weights are relatively small. Now, if we split this data into equal quantiles, we would put a quantile here and here. But remember, we are treating each quantile as a unit, and lumping the last 2 observations together as a unit means they will end up in the same leaf together in the tree. And since the positive residual will cancel out the negative residual, it will be very difficult to improve the predicted probabilities. So, instead of using equal quantiles, XGBoost tries to make quantiles that have a similar sum of weights. In order to divide the observations into quantiles where the sum of the weights are similar, we divide them into these quantiles. The sum of the weights in the first quantile is 0.18. The sum of the weights in the second quantile is 0.18. The third quantile only has one observation, and its weight is 0.24. And the last quantile only has a single observation, and its weight is 0.24. By dividing the observations into quantiles where the sum of the weights are similar, we split the two observations with low confidence predictions into separate bins. In other words, the advantage of using the weighted quantile sketch is that we get smaller quantiles when we need them. Bam! So, when we have a huge training dataset, XGBoost uses an approximate greedy algorithm. And that means using parallel learning to split up the dataset so that multiple computers can work on it at the same time. And a weighted quantile sketch merges the data into an approximate histogram. And the histogram is divided into weighted quantiles that put observations with low confidence predictions into quantiles with fewer observations. Note: before we move on, I want to mention that XGBoost only uses the approximate greedy algorithm, parallel learning, and the weighted quantile sketch when the training dataset is huge. When the training datasets are small, like the ones in my examples, XGBoost just uses a normal, everyday greedy algorithm. Bam! Now let's talk about Sparsity-Aware Split Finding. So let's return to the example where we were using dosage to predict drug effectiveness. Only this time, we have a few missing values. Even though we have missing values, we can calculate the residuals, the differences between the observed drug effectiveness and the predicted drug effectiveness, using the initial prediction, 0.5. And just like we normally do when we build XGBoost trees, we can put all of the residuals into a single leaf. Now we need to determine if splitting the residuals into two leaves will do a better job clustering them. So, just like we always do for continuous data, we need to sort the dosages from low to high. Unfortunately, it's unclear how to sort the dosages with missing values. So, what we'll do is we'll split the data into two tables. One table will contain all of the observations with dosage values, and another table will contain all of the observations without dosage values. Now, focusing on the table that has dosage values for every observation, we sort rows by dosage from low to high. Now we test the average of the first two dosages, 7.5, as a candidate threshold. Note: if this was a large dataset, we would be using the first quantile here. In this case, we test the threshold by putting the residual for the one observation that has a dosage less than 7.5 in the leaf on the left, and put the remaining residuals, which all have dosages greater than 7.5, into the leaf on the right. Now that we have all of the residuals with known dosages in the tree, we calculate two separate gain values. The first gain value, which we will call gain left, is calculated by putting all of the residuals with missing dosage values into the leaf on the left. The second gain value, which we will call gain right, is calculated by putting all of the residuals with missing dosage values into the leaf on the right. Now we do the same thing using the average of the next two dosages, 15.5, as a candidate threshold. We put the residuals with dosages less than 15.5 in the leaf on the left, and the residuals with dosages greater than or equal to 15.5 in the leaf on the right. And then we put all of the residuals with missing dosages into the leaf on the left and calculate gain left. Then we put all of the residuals with missing dosage values into the leaf on the right and calculate gain right. Lastly, we do the same thing using the average of the last two dosages, 23, as a candidate threshold. We calculate gain left, and we calculate gain right. In the end, we choose the threshold that gave us the largest value for gain overall. In this case, that meant picking gain left when the threshold was dosage less than 15.5. Note: this path, going to the left leaf when dosage is less than 15.5 will be the default path for all future observations that are missing dosage values. For example, if this was the XGBoost model, and we got a new observation without a value for dosage, but we still needed to predict drug effectiveness, then we would assume that this observation goes to the leaf on the left. Thus, Sparsity-Aware Split Finding tells us how to build trees with missing data and how to deal with new observations when there is missing data. Double bam! Now we need to talk about CacheAware Access. This is where XGBoost starts to get super nitty-gritty. The basic idea is that inside each computer we have a CPU, a central processing unit, and that CPU has a small amount of cache memory. The CPU can use this memory faster than any other memory in the computer. The CPU is also attached to a large amount of main memory. While the main memory is larger than the cache, it takes longer to use. Lastly, the CPU is also attached to the hard drive. The hard drive can store the most stuff, but is the slowest of all memory options. If you want your program to run really fast, the goal is to maximize what you can do with the cache memory. So XGBoost puts the gradients and Hessians in the cache so that it can rapidly calculate similarity scores and output values. Bam! That was pretty simple. Lastly, we need to talk about blocks for out-of-core computation. Going back to the super simple computer schematic, when the dataset is too large for the cache and main memory, then, at least some of it, must be stored on the hard drive. Because reading and writing data to the hard drive is super slow, XGBoost tries to minimize these actions by compressing the data. Even though the CPU must spend some time decompressing the data that comes from the hard drive, it can do this faster than the hard drive can read the data. In other words, by spending a little bit of CPU time uncompressing the data, we can avoid spending a lot of time accessing the hard drive. Also, when there is more than one hard drive available for storage, XGBoost uses a database technique called sharding to speed up disk access. For example, if this is the dataset and it is very large, then XGBoost splits the data so that each drive gets a unique set of records. Then, when the CPU needs data, both drives can be reading data at the same time. Bam! Thus, CacheAware Access and blocks for out-of-core computation are optimizations that take the computer hardware into account. Lastly, I need to mention that XGBoost can also speed things up by allowing you to build each tree with only a random subset of the data. And XGBoost can speed up building trees by only looking at a random subset of features when deciding how to split the data. Bam! In summary, XGBoost is fast for a lot of reasons. Some of these reasons, like CacheAware Access, are not even vaguely related to statistics. And that makes XGBoost something more than just an applied statistical technique. And that means machine learning is more than just applied statistics. Triple bam! Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to my Patreon campaign, becoming a channel member, buying one or two of my original songs or a t-shirt or a hoodie, or just donate. The links are in the description below. Alright, until next time, Quest on!